So in the last lecture, we have seen various examples of different topologies, and you might have noticed that it's a bit tedious to check all the properties for a collection to be a topology. And so it would be nice to have a method which is simpler than giving explicit descriptions of the collections of sets which form a topology. And one of these methods is through what's called a basis for a topology, and this will be the topic of our lecture today. So let us see what is a basis. So let me define a basis. A basis for a set X is a collection of subsets of X let me call it B, which satisfies the following conditions. So the first condition is that given any point in this set X, there exists an element or a member of this collection B such that X belongs to this member B. So any point in X is a member of at least one of the elements of this collection B. The second property that it should satisfy is that given two members of this collection B, B1 and B2 in B, such that and any point X in the intersection of these two sets B1 and B2, there exists a third set B3 which belongs to this collection such that you have X is a point in B3 and B3 is a subset of B1 intersection B2. So if we just see a Venn diagram here, so you have B1 and B2 and X belongs to the intersection of these two sets. Then there is this third set B3 which contains X in the collection B, which contains X, and it is contained inside the intersection of these two sets. So this kind of a collection is called a basis which satisfies these two conditions. And so let us see what is the point of having such a construction. So define tau to be the collection of subsets of X such that for any X in U, there exists a member of this basis B such that X belongs to B and B is a subset of U. So this is a collection of subsets of U, and since we denoted tau, you might have guessed that this will form a topology on X, and this is indeed the case. And let us show that this collection tau is a topology. So then let me state this as a theorem, theorem 3.1. The theorem says that this collection tau is a topology on X. Okay, so given a basis, we defined collection tau, okay, which is the collection of all subsets of X, for which if you take any point in this subset, then there exists a basis element which contains this point X, and it is contained in U. Okay, and I claim that this is a topology on X, and tau will be called the topology generated by the basis B. Okay. So first thing to note before we go to the proof of this theorem, so note that if you take any basis element in B, then B automatically belongs to this collection tau, and in particular, once we have shown that tau is a topology, then any basis element are open because they belong to the topology. So this is just a side note which will come in handy later on. And so let us see a proof of this theorem that tau is indeed a topology on X. So to check that tau is a topology, we begin verifying the various conditions for tau to be a topology one by one. So the first thing that we want to show is again that phi and x are in tau. So let us check this. So first of all, x belongs to tau. Why? Since from property 1, from the first property of the basis, so let me go back to the definition, which says that given any x, there exists a basis element such that x belongs to that basis element. So we have defined our topology as the collection of subsets for which, given any point in that subset U, there exists a basis element such that it contains the point and lies inside this set U. And so if you take U to be X here, X the whole set X, then for any point in the space X, of course there exists a basis element B which contains the point, and which is of course a subset of X. So therefore the condition for a set to be open is satisfied by the set X. So from property 1, which says that given any x in X, there exists a set B such that X lies in B. So of course if U is X in our definition of the collection tau, then X is, so if you choose such a basis element here, then X belongs to B, and which is a subset of X. So X is in tau. So we see that the space X itself is in tau. Why is the empty set in tau? Well, this is since the condition for a set U to belong to tau is vacuously true for the empty set. Why? Because tau is the collection of sets such that for every x in U, there exists a basis element in B such that x belongs to B is a subset of U. So for any x in U, right? But if U is empty, then this whole statement is vacuously true. Vacuously true for U to be the empty set. Okay, because there are no elements in this set, so this property holds vacuously. It's vacuously true. So this implies that the empty set is in tau. Now let us check for finite intersections. Finite intersections. So let's start with two sets. Let U1 and U2 be two sets in this collection tau already. Then we want to show that U1 intersection U2 belongs to tau. So this is to show. So this is the same as saying that given X inside U1 intersection U2, there exists a basis element such that X belongs to B and it is a subset of this intersection. This is what we want to show. So because U1 and U2, since U1 and U2 are already in this topology, in this collection tau, so if X belongs to U1 intersection U2, then of course X belongs to U1, which implies that there exists a basis set B1 such that X belongs to B1 and it is a subset of U1, and X belongs to U2 implies that there exists a basis set B2 such that X is in B2 and is a subset of U2. And so taking these two conditions together, we see that X belongs to U1 intersection U2 implies that X belongs to B1 intersection B2 and this is a subset of U2. So these two are the conditions that I wrote here are from property 1 of the definition of basis. And now we have that X belongs to the intersection, but notice that the intersection is not automatically a basis element, but from property 2 of the definition, there exists a B3 in B such that X belongs to B3 and it is a subset of B1 intersection B2 and this is a subset of U1 intersection U2. So we have used both the properties for the definition of a basis here. The first one to find these basis elements B1 and B2, and the second one is to find a basis element B3 that lies inside the intersection B1 intersection B2. So we proved this. So U1 intersection U2 belongs to this collection. And now for a finite arbitrary finite intersection, if U1 U2 Un belong to tau, we need to show that the intersection Ui equal to 1 to n is in tau. Okay, and this is simply by induction. So we have already seen, so let's take the base case as U1 intersection U2 is in tau. Okay, this is the base case, and the induction step is that if U1 intersection U2 intersection Un is in tau, then U1 intersection U2 intersection Un intersection Un plus 1 belongs to tau. So given that any infinite intersection of n number of sets in tau belong to tau, then finite intersection of n plus 1 number of sets in tau also belong to tau. So the induction step can be shown just by noting that u1 intersection u2 intersection un intersection un plus 1 is the same as u1 intersection u2 intersection un first, and then taking the intersection with un plus 1. Now we already know from hypothesis that this belongs to tau. Okay, this is what the induction step hypothesis is, and this also belongs to tau. And we have shown from the base case that the intersection of two elements belong to tau from the base case. So this implies that the intersection I equal to 1 to n plus 1 of ui belongs to tau. So finite intersections can be handled just by taking an induction argument. Similarly, if you want to check arbitrary unions, so take u alpha indexed family of sets in tau, and to show that this arbitrary union of these u alphas belongs to tau. So again, what this means is that given any point in this union, there exists a basis set B. There exists a basis set B such that X is in B and it is a subset of this union. So how do we find this set B? Well, X belongs to this union U alpha implies that X is a member of U alpha for at least one alpha, and this implies that there exists a set B, basis set B, such that it contains X and it is a subset of U alpha. Okay, for say if you say alpha equals alpha naught, then this set B is this subset of U alpha naught. Okay, so now we have found this basis set, and of course this also implies that X belongs to B and it is a subset of the union of these U alphas. Okay, because B is a subset of U alpha naught and U alpha naught itself is a subset of this arbitrary union, so X is in B and B is a subset of the arbitrary union. So this implies that a union U alpha is in tau, and this concludes our proof that tau is a topology, on X. And as we said, this we call it the topology generated by the basis elements, generated by the basis B, or sometimes also induced. So both these terminologies are used: topology generated or induced by the basis B. Now let's see what are some examples of basis. So the first example is for a set X. For a set X, we define our collection B to be the collection of all singleton sets. So this is an indexed collection, indexed family of sets, which is just each of these member sets is just a singleton set, and the family is indexed by the set X itself. And so this is a collection of subsets of X, and it is easy to show that this is indeed a basis. For example, if you want to show that for each So property 1, for example, for the definition of basis is that for each x in X, there exists a basis element in B such that X is an element of this set B. And this is true because, well, we can take B to be the singleton set itself here. So of course X belongs to this singleton set. So property 1 is valid. So property 1 is valid. Now we can also check property 2 for the definition of a basis. So it says that given B1 and B2 basis elements, then there exists for any point X in B1 intersection B2 a basis element B3 such that it contains X and it is a subset of B1 intersection B2. So let's see why this is true for our collection of singleton sets here. So so if B1 is of the form, say, X1 and B2, because they are basis sets, so they must always be of this form by definition, and it is of the form X2, so B2 is of the form X2, and X1 is not equal to X2, then B1 intersection B2 is empty. So this condition, X, for any X in B1 intersection B2, there exists a basis element which contains this is vacuously satisfied if X1 is not equal to X2. So property 2 is vacuously true for this case. And if X1 is equal to X2, then B1 intersection B2 is the set itself. So they are the same. If B1 equals to X1 and B2 equals X2, and X1 is equal to X2, well, this implies that B1 is equal to B2. So B1 intersection B2 is the same set X1 or X2, so let's call this X, and so this is already a basis element, and of course this is contained inside B1 intersection B2, and so property 2 holds in this case as well. So we see that this collection B is a basis, and so the question arises, what is the topology generated by this basis? So I claim that the topology generated by B is the discrete topology that we have seen before, which was the collection of all subsets of X. So why is this true? Well, let's see from the definition of the topology generated by a basis. So this is the collection of all subsets such that for any X in U, there exists a basis element in B such that X is contained in B and B is contained inside U. So I want to show that all subsets of X are open, and this is the same thing as saying that the topology is the discrete topology. So for any subset A inside X, if X is in A, then the basis element of the singleton set X itself contains X, and it is inside A. It is a subset of A. So this means that A is open. And this means that tau is the collection of all subsets of X. Because A was arbitrary, we deduce that tau is the collection of all subsets of X, and so we see that this basis of singleton sets generates the discrete topology on X. And now we will see other examples of basis and topologies on the set of real numbers in the next lecture.